Okay, we started chapter 2 last time, and we'll continue. Hopefully, we can finish chapter 2 today. Chapter 2 is mostly review on magnetic circuits. I'm going to do that part briefly, or not briefly, but fast. And the more important part of the chapter is toward the end. I'm going to spend more time on that one, or I'm going to go slower on that one. That's going to be on air gap and the benefits and drawbacks of having air gap in the core. Okay, so let's review this. There's going to be another review after this chapter. Chapter 3 is going to be review on DC to DC converters, but specifically related to the magnetic portion of the DC to DC converters. So I think it'll be good. It'll be a good review even for those who took EE433 last fall. Right? But let's finish this one first. This is a topic that you learn in 255, right? So finding or solving for magnetic circuit, basically, right? So we talked about the benefit of obtaining the equivalent circuit, electric circuit, for the magnetic for the magnetic design, right? And here in magnetic design, you are dealing with flux density, field intensity, geometric structure of the core. But then we can transform those into the language that we understand more, which is the electric circuits, right? So that was the explanation that I did last time. So here's an example where we would like to find reluctance in the rectangular core, right? And here is the structure of the core, right? Rectangular core, and there's the winding, right? And then you can see there are 4 sides of the core, and each side here is, or each side of the core represents its own reluctance, and all 4 sides may or may not be having the same reluctance depending on the physical dimension of this structure, right, or this core. Okay, and then we talked about the MMF, which is N times I, right? That's in electric circuit, we call the analogy would be the voltage, independent voltage source, but here in magnetic circuit we call it MMF, and that's N times I. All right. So the reluctance of a core, right, that's equal to, we talked about this as well, but we covered this last time. That's LC over mu A, right? So L is the length, mean path length of the core, mu is the permeability, and A is the cross-sectional area of the core, right? And as I said earlier, we have 4 different sides, right, for this core: left leg, top side, right leg, and bottom side. And side 1, or the left leg, has its own length. Let's call it LC1, and cross-sectional area, which is A1, right? Same thing with the top side, right leg, and bottom side, right? Each has their own length and area, cross-sectional area, right? Such as, this is the length, and the cross-sectional area would be, if you were to cut this core, right, then there's the cross-sectional area of the core, okay? Then recall that, or notice that for this example, each of the segments, right, all four, I should say, all 4 sides have the same length of 15 centimeters, and just call it LC. Is that true? Let's double check quickly. 10, you can see that we have 10 from here to here, and then you have 5 here, 5 there, but then we want to get the mean, right, the mean path length of the core. So we want to take the middle point of 5. So that's 2.5 on each side, right? So that's going to be 2.5 on this side. That's half of the 5, and then another 2.5 on the right side. That's also half of the 5. So therefore, 10 plus 2.5 plus 2.5 gives you 15. Right, and you can see that that's the same all around the core. Okay, So in that case, this is a simple case where the core is symmetrical all around, right? So that's going to make it simpler to calculate the reluctance, right? So L is going to be equal to all four sides, and let's call it LC, and that's equal to 15 centimeters. Cross-sectional area, E5 by 3. Is that correct? Let's check. Yeah, so right here, that's an example of a cross-sectional area, right? Right there. So the width is 5, the length is 3, or the depth is 3, right here, right? So the depth is 3, the width is 5, so therefore the cross-sectional area is 5 by 3. So that's correct. And then the way we deal with the reluctances is that for rectangular core or for any other geometry, right, or shape, we can treat each of the sides as a single individual reluctance, but then at the end you can combine them, right, depending on the structure, of course. In this case, it's only a rectangular core, right? So here's the reluctance from the left leg. That's from the top side. That's from the right side, and that's from the bottom side, right? So each is being represented by their own reluctance. And so when you draw the electric circuit model of these magnetic circuits, then you can just put them in series, right, as you can see. So then, just like in electric circuit, you could, when you have resistances in series, you can just add them up, right? So then you have equivalent resistance, or in this case, equivalent reluctance, right? So that's how you deal with multiple reluctances in a core, right? So you just add them up. All right, and that's equal to, do I have the answer here? Yes. R total is equal to R1 plus R2 plus R3 plus R4. That's going to be equal to 4 over mu. Okay. So that's the answer for that example. This next one, you can see it's not symmetrical, right? It is, if you look at top and bottom, and also left and right, but you can see that the bottom side, for example, is not symmetrical compared to doesn't have the same width as the side, the ones on the sides, right? So the top and the bottom, they're symmetrical or the same width, or length, but then the left and the right, they have different length or width, right? So same thing, right? You deal with this with the same approach, right? You represent each of these segments, right, as its own reluctance. So this segment right here, that's one reluctance. The segment on the right, another reluctance. Top, another reluctance, and left, another reluctance, right? So, also the cross-sectional area, right, might be different as well. It looks like they are different, right? But anyhow, the total reluctance, I should say, should be the summation of all reluctances, right? That's going to be R1 plus R2 until R4. And R1 is LC1 over mu A1. So that's going to be on the left side, looks like. That is our R1 right here, right? And so make sure that the length that you put in there corresponds to the mean path length of the segment on the left, right? And then also A1, that corresponds to the cross-sectional area of the left segment of the core, right? So in that case, that's going to be, what is it? That's going to be 10 by 4, right? For the left and for the left side of the core, yeah, it is 10 by 4. Okay. And then, yeah, same thing with R2, R3, R4. You just have to be careful on what to put in on the L and the A, right? Let's just do one more. Let's say we look at the bottom side, right? The bottom side is R4. What is the length of R4? That's going to be 20, right? Plus halfway of the left and halfway of the right there, right? So half of 5 is 5 right there. So that's going to be 5 right here. Half of 5 is 2.5, right there. So therefore, the length of R4 that you put in, right, LC4 right here, that should be 20 plus 5 plus 2.5. What is that? That is equal to 27.5. Or is it? 20 plus 5 plus 2.5. Okay. Yes, it is. All right, right there. And then how about the area of the bottom side, the cross-sectional area? I didn't draw it correctly, but if this is the bottom side of the core, what is the cross-sectional area of that? Well, that's going to be the width, which is 10 right there. Right, yeah. Wait. It is, yes. The width is 10, so that's this side right here. That's 10. And then the depth is 4. So it should be 10 by 4. Is that right? Yeah, it is. 10 by 4. So 40. Okay, any questions on this? Again, this is just a review. So you, am I right that you learned this in 255, just to make sure?
Yeah, I remember that.
Okay, good.
I actually do have a question.
Yeah, go ahead.
Is there a reason that in this last example, it was converted to meters, but not in the previous example?
I didn't notice that. Hang on. For the previous example, I didn't put the unit, looks like.
Oh,
right?
okay.
Yeah, so just keep in mind that that's still not converted into SI or MKS.
Oh, yeah, I think I was assuming centimeters. Okay, thank you.
Okay. So yeah, this one yeah, you're right. This one I use the MKS, I believe, right? M turns per Weber. Yes. So I have to convert to meters. All right. Next example, determine the flux density B. So this is again another example where you are analyzing the magnetic circuit. That's our magnetic circuit, right? Using electric circuit. In this case, to determine flux density in each leg of the core, right? So flux density in each leg. So from here, over here, and over here, right? So those are the three values that we need to find. First of all, keep in mind that we can always, we can transform this into electric circuit, right? And before we solve this problem, right? Man, which I think it would be good to have a poll right now, huh? Thing is, I have not set up the poll yet, but that's okay. We'll do it next time, maybe. Before we even solve this problem, I was gonna say we should be able to kind of predict, right, which one has the highest flux density, right? Which one? Which leg? The left, the center, or the right?
The left.
The left. Why is that?
Is it the source of the other flux?
Yes, because it is the MMF, right? This is the one that produces the flux that would then split, right? But then you got to be careful as well that flux density is a function of A, right? So when it comes to flux, I should probably ask more specifically about flux. But for this one, yeah, left should be the highest. But when it comes to flux, right, flux, not flux density, for sure, right, the one on the left will be the most, right? Because that's the total flux basically, right? So if you think about flux is analogous to current, right? Then this is the total current right here, right? Oh, actually it's downward, right? Yes. So current or flux goes downward, right? That's the total flux, and then that flux splits, right? Just like current will split, right? So therefore by KCL, quote unquote KCL, I know that the flux, the total flux must be bigger than the total flux on the left must be bigger than the flux in the middle and the flux on the right side, right? Before we even solve the problem, right? And that's a good way to check as well, right? If you have a problem like this, right? And then at the end, you get flux on the left to be less than the flux in the center, then you know that something's wrong, right, with the calculation, right? So I think that would be a good way, again, to kind of check to see if you had a mistake in the calculation. So we'll see if that's the case here, right? Let's see if I make the mistake. But do you all agree that that flux on the left should be the highest? Yes, right, should be. All right. Okay, let's do this. So what is it asking again? But it is asking flux density, not flux. Okay. So I have the Ni, MMF right there, right? And then from there, I should be able to calculate for for the flux density there, because I have the A. Sorry, let's go back. I have the physical dimension of the core, as you can see, right? The depth is also given. The mu r is also given to be 1200. Okay, good. So we should be able to solve this problem relatively easy. Right? For each leg, we know that flux density is flux over A, but flux by itself is Ni over R, right there. So that's why I said earlier that we should be able to calculate for the flux, because we know what Ni is, right? And reluctance is going to be a function of the geometric shape of the structure of the core, right? R by itself is LC divided by mu A, as we already know. And so for this example, we can define different segments, right? Oh yeah, I think that's important as well. Many ways to solve this problem, right? And in this example, the way I did it is let me use a thicker line. Okay. So I divide it into 3. I believe this is the first segment that I did, right? So I consider that is the first segment, and then the segment means it would represent a reluctance, right? So the one that I just draw, that's going to have its own reluctance, and then the one in the middle right there, that's the second segment, is going to have its own reluctance, and the third one is going to be another reluctance. That's going to be this last segment right here, right? So I should have 3 reluctances, right, representing those 3 segments. So that's what I have right here. Oops, no, I don't need to have make it thinner again. Okay. And then, oh yeah, and then we have L1 and L2 due to symmetry, they're equal. So if we check here, you can see that the left segment and the right segment, they're symmetrical. If you look at the physical length or dimension, right, of the core, they're symmetrical. So even though the picture doesn't actually show that, but if you look at the numbers, the left segment should be equal to the right segment, right, symmetrical. So therefore, the length of the left segment should be equal to the length of the right segment. Okay. And the area too. I put R1 equals to R2. That means the area is the same too. Then let's check. 9 here, 9 there, 9 here, 9 there. Okay, yeah, they are the same. So I should note that L1 is equal to L2 and A1 is also equal to A2. So because of that, then reluctance R1 must equal to reluctance R2. What about mu? Because remember, R is equal to LC over mu A. If L is the same, A is the same, what about mu? Well, that would depend on the material, right? So in this case, it is still the same core, right? So therefore the material is the same. So therefore all throughout, this core, mu should be the same. Okay. All right, so then the solution takes the following 3 different steps. The first one is draw equivalent circuit, which represent our magnetic circuit, and then calculate the reluctance by using the mean path length, and use KVL, KCL to solve for flux. And then once you get the flux, then you can get flux density. How? By dividing flux with the area, cross-sectional area of the segment, right? So here's the equivalent circuit as I explained earlier, right? There are 3 different segments: the left, the right, and the middle, right? Or the center. Reluctance on the left side, right there, R1 should be equal to the reluctance on the right side, okay? Because they have the same length, the same depth, right? So right here, without going through the details, those are the lengths for each segment. You can double check, right? When you review this example, let me know if I make any error, okay, or if I make any typo on this calculation. All right, so L1, L2, L3, those are the length. Those are the areas, sorry, these are the areas. As you can see, A1 is equal to A2, right? And then A3 is the center segment, right, that has different area. All right, so then length number 1, let's see, that's okay. Length number 1, there should be 3 segments. Let's go back here. Right, so I'm looking at the segment on the left. There's the segment on the left that consists of 3 smaller segments, right? 1, 2, and 3. Right, so 1, 2, and 3. Right, so you can see 1 and 3 smaller segments. They're the same, right? The same length, 25 plus 9 divided by 2 plus 15 divided by 2, right? For the top and the bottom segments. On the left, for the left segment, the length is 25, right there, plus 9 half divided by 2 plus 9 divided by 2. So that's going to be 25 plus 9. So I have the smaller segments, right, twice, plus 1 that has 9 plus 25 as the length. Let's check here. Yes, right there. That's the left, right, segment, and this is the top and the bottom segment. There's 2 of them. Okay, so that looks correct to me. And then L2 is equal to L1 due to the symmetry, right? And then we have L3, the length in the center part of the core. And let's check to see if this is correct. Okay, that's the length of the center segment. That's going to be, yeah, the same as the of this segment right here that we did earlier, right? That's going to be 25 plus 9 over 2 plus 9 over 2, right? So that's going to be 25 plus 9. Is that what I have here? Yes, right there. Okay, so now I'm done with A's, I'm done with L's. So now I can just get the reluctance, right? Reluctance 1, which is equal to reluctance 2, is L1 over mu A1, right? That's the equation, the answer or the value for reluctance number 1. Again, that's the same as reluctance number 2. And the reluctance number 3, that's the center core, same thing, L over mu A. And we already calculated L3 and A3, right? Okay, so you can see kind of tedious, right? Going through this, just like going through circuit analysis, right? Okay, once we get all 3 reluctances, right? Then we could simplify, or not simplify, yeah, we could get the equivalent circuit. Imagine if this is our circuit right there, then how do you find the current, the total current? So if you have all three resistances, right? If you know the value of all 3 resistances, then in order to get the total current, if you know the voltage here, right? You know the voltage, right? Let me erase that. So you know the voltage, you know the resistor values, right? But you don't know what the current is. What do? Well, we're gonna one way is to simplify the circuit, right, by getting the equivalent resistance, right, of all of these three resistances, right? How so? Well, you can see from here, these two are in parallel, so I could combine those, and once I combine those into one single resistance, then I could put those two in series, right? That's what I would do. Then once you get those, once you transform those three into one single equivalent resistance, then you can just do Ohm's law to get the current, right? I is equal to V over R total in this case. So same thing here, right? That's why it is nice to be able to represent magnetic circuit with electric circuit, right? Because we've done this thousands of times, right? So now you can see that we already combine all reluctances into one, right? This is the one that we are looking for, right? And we know this one, we should know this one now. That's just R1 plus, you see that R1 plus the parallel combinations of R2 and R3. That's going to give us the total reluctance, right? And again, following Ohm's law in this case, right, quote unquote, and you get the flux right there. That flux is equal to Ni over R, right? The MMF divided by the total reluctance. That gives you the total current right there, right? So that's the total current on the left side of the core, okay? But again, the question is asking for flux density, not flux, right? This is flux. So flux density is equal to flux by itself divided by the area of the core, cross-sectional area of the core, right? And so we already found this earlier, that the cross-sectional area of the core on the left side is 9 by 5, right? So then let's go ahead and divide the flux that we just calculated with the area. That gives us 0.482 Tesla, right? Now you have to go back to the original circuit, right, to find the other fluxes, right? And as I explained earlier, right, the nice thing about electric circuit is that we understand how to solve electric circuits, right? So now we can apply concepts that we learn in electric circuits into this magnetic circuit, right? It's really convenient, right? For example, here is where we want to find the MMF is right there, the flux, the reluctance right there, right? And then we have another reluctance right here, and then another reluctance right there, right? I believe this is number 2, this is number 3, and this is number 1. And now I know this flux, right? We just calculated that flux. Let's call it flux number 1. And now I want to know flux that goes into R3 and flux that goes into R2, right? How do we do that? Oops, that's not flux, that's Q. Well, again, luckily we can view flux as current, right? So to us, we are familiar with the concept of current division, right? So if we have a total current I1, in our case, flux 1, then if it splits into two different paths, right? Two different currents, let's say I2 and I3, then I could apply current division, right? To find I2 and I3 right there, okay? And so that's what I did here, right? That's what I did right here is that I can find flux number 3 using the current division, quote unquote, right? And then I get 1.826 milliweber for the flux. And you can see the flux density then is just going to be that flux divided by the area of the center. This is on the center, right? Because 3 is on the center, okay? And then same thing for the second flux, flux number 2, which is on the right side, right? Using flux or current division, right? We get 0.344 milliweber, right? And then again, the question asks for flux density, so therefore you divide it by the area, cross-sectional area of the right segment. That gives you 0.076 Tesla. All right. So here I ask, even though L1 is equal to L2 due to the symmetry, but we can see that flux 1 is not equal to flux 2, right? What was flux 1 again? That's the total flux, right? What is it? 2.17 milliweber. So why is that? Well, again, as I explained earlier, because flux 1 is the total flux, right? Because that's the one that has, that's the segment that on the side, that's the segment of the core that has the MMF right there. So it should give us the most flux right there. So as we expected, right, before we start this problem, right? Before we started this problem, we should expect to see that flux number 1 should be larger than flux number 2, should also be larger than flux number 3. And that's what the answer that we have here prove that, right? And in terms of flux density of the left side, that's going to be 0.482. And then the center, or not center, but the right side is 0.076. And the one in the center is 0.243. Okay. Any questions on this? All right, this next one gets more complicated, right? Because now you can put more MMFs, right, such as a transformer, right? And remember, in inductor, you have only one winding. But what about transformer? Right? Transformer has at least two windings, right? So 2 windings means that you have 2 MMF, right, applied into the core, right? Even though the other current is actually being, what do you call it? Even though not current, but voltage, right? If you apply current here, then you're going to induce voltage here, right? But then still though, right? If you just leave it open, right, then of course there's no current, right? But if you connect a load, now it's going to draw current, and that current multiplied by the number of turns gives you another MMF, right? Makes sense, hopefully. So again, that's in case we have a transformer, right? Let me just redraw that here, the one that I just discussed. So for a transformer, you should have at least 2 windings, right? And then let's say that this is the one that I connect to a voltage source, right? Then that's the one that's going to inject current, right, to the first coil on the left, right, or primary side, if you will, right? If you do that, then as you know, flux is going to be produced in the core, right? And in the process, we'll pass through the second coil, is changing flux with respect to time. So that's going to give us induced voltage on the secondary side, right? And this induced voltage or this coil is not going to have any current if you leave it open, right? Just like when you leave the secondary side transformer open, right? There's not going to be any current until what? Until you connect it to a load. Once you connect it to the load, then you have current flowing to that load, right? And that current flows through this winding on the secondary side, right? So that current times the number of turns on the secondary side, that gives this core another MMF, right? So I just want to explain, practical example of this case right here, right? So again, this is commonly found, right, in many applications, because many transformers are out there, and so that's why this example is also important for you to review, right? Having 2 MMFs, right? Okay. So what do we do here? Again, luckily we can convert this into or transform this into electric circuits, right? So therefore, the top winding that would represent 1 voltage source, and the bottom winding, that would be represented by another voltage source, right? And then connected by resistors, right? Or in this case, reluctances, right? So the one thing that is important when you have MMF is that you need to know the direction of, especially when you have multiple MMFs, right? You need to know the direction of, not the direction, sorry, the polarity of MMF, right? And we already talked about it last time, right? Using right-hand rule, right? Right there, I already have the polarity there, but I was going to ask you actually. So the polarity is going to be how for the top winding? If you use the right-hand rule, I'm doing it right now, that's going to be plus here and minus here, right? So that's important, right? Because that's going to determine how current flows when you have the equivalent circuit, right? If you have the voltage flip, then you're going to get different answer, right? For the flux, or in this case, for the circuit, is going to be current. All right, so what about this bottom winding right there? What is the polarity of the bottom? What is the polarity of MMF caused by the bottom winding? So again, I'm using right-hand rule. So that should be plus here, minus here. Do you agree? Well, let's check my answer. Yes, so it is the same as my answer, right? So the top one is plus minus that way, but the bottom one is minus plus that way. Okay. So then you draw the equivalent circuit with the correct polarity of the MMF, right? Right there and right there. And then you have the segments, right? Again, I'm dividing it into 3 segments. 1 right on the left, 2 on the center, and 3 on the right-hand side of the core, right? So 3 segments means 3 reluctances. And that's what I have: left, center, and right. Yeah, just like this, right? So then how do you solve for, what is it asking, first of all? Find the flux densities again, right? Yeah, find the flux densities. Find flux densities in each leg, in the right, center, and the left legs. Okay. So yeah, you need to think of it as an electric circuit, right? And so you can do, you can approach it in several ways. And in this case, I use the loop equations, looks like, right? KVL, right? So you have 2 loops here. So I'm going to assume that the flux, right, which is equivalent to our current, is going counterclockwise on the left-hand loop. And then the second flux on the right-hand loop is, I'm going to assume that that's going to flow counterclockwise as well. Okay. Does it have to be counterclockwise? Well, as you learn from circuits class, it doesn't have to be, right? You can do clockwise, whatever it is. At the end, you're going to get the same answer. All right. Step number 2, compute the reluctances. Right. I won't go through this because you know by now how to do it, right? Quite tedious, as you can see. And then, okay, and then what is it? Right there, sorry. Then step number 3, once you already found the reluctances, then you can apply KVL, right? In this case, we have left-hand loop and right-hand loop, right? On the left-hand loop, what do you have there? Let's check. What happened there? Sorry about that. Okay, left-hand side. Okay, left-hand loop, you can see that we have 1000, right, equals flux 1 times RL, right? And then flux 1 minus flux 2 times RC. See that, right? So 1000 is equal to flux 1 times RL plus flux 1 minus flux 2 times RC. So that's what I should have for left hand loop. Yeah, right there. Okay, any question on that one? Okay, so then I have one equation, two unknowns, right? Because I already know RL and RC, right? But I don't know what flux 1 and flux 2 is, right? So just leave it like that, right? When you simplify the algebra, you get one equation, two unknowns right there, right? So we need another equation, right? That is similar to this. If I have two equations, two unknowns, then I could solve for flux 1 and flux 2. Where do we get the second equation? None other than from the right-hand loop, right? If you look at the right-hand loop, similar, right? You have 4,000 equals flux number 2 times RR plus flux number 2 minus flux number 1 times RC. You agree with that? So that's what I should have. 4,000 flux number 2 R plus flux 2 minus 5. Yeah, okay, good. Anybody disagree with this equation from the right-hand loop? All right, from here you can see that I have reluctances already calculated, right? So the only unknowns here are flux 1 and flux 2. So if I arrange the equation, rewrite it in the same way as equation number 1, then now you can see that we have another equation with two unknowns, right? The same two unknowns, flux 1 and flux 2, right? So if you combine it with equation number 1, you should be able to solve for flux 1 and flux 2, right? In this case, flux 1, the answer is 17.67 milliweber. Flux 2 is 41.23 milliweber, right? And then flux number 3, which is on the center leg, in the center leg, that's going to be flux 2 minus flux 1, right? That's 23.56. So, did it again. Okay. Any questions on these three fluxes? Okay, so then the question is asking for flux density, not flux. Okay, so be careful. Flux density. These are all fluxes. Right? Flux density would be flux divided by the area of the core. Right. So for the left leg, flux 1 divided by cross-sectional area on the left side of the core. That's going to be 3.5 Tesla. And then right leg is going to be 8.24. And the center leg is going to be 4.712, right? Any questions? And hopefully you can see that. Hopefully you can see the importance of knowing how to determine the polarity of the MMF, right? Because if the MMF is flipped, right, and somehow we didn't determine correctly, right? If this is minus plus by mistake, then you're gonna get a different answers, right? Because the equation and the sign in the equation will change, right? Okay. Any questions on this? All right, not. Let's move on. I wonder what happened again here. Oh, air gap already. Yeah. It jumps again. Ah, something is screwy today. What's going on? Okay, that's done. That is done. That is okay. Air gap. Okay. Right here. Now the next topic right here, it's introducing air gap. Right. I believe you also covered this in 255. Right. So you have a core with an air gap. Right. And I'm not sure if you cover the concept, not the concept, but the practical use of air gap, as well as why you need to learn why is it that you need to learn magnetic core with air gaps. If you didn't do that, then we'll cover it here. Okay, so we'll do that next. Okay, so then here, theoretically speaking, you could add an air gap, right, in the core, such as this one right there, right? And just like the name implies, right, this air gap means that the core is being interrupted, basically, right? So you have a magnetic material right? And you have flux flowing into this magnetic material, and then its flow is being interrupted by having a different permeability, right? Because now this flux has to flow to the other side, right? To this side of the core, right? Through a material that has different permeability. In this case, permeability of air, right? Which is close to mu naught, roughly mu naught, right? Okay, so from mu to mu naught, right? So that corresponds to the what do you call it? A different reluctance, basically, right? So you have a different reluctance, or in circuit language, it's going to see different resistance, right? As it is flowing through this air gap. Okay. Now the air gap itself should be much less than the dimension of the core, x and y. What is x and y in this case? I think it's the width and the depth. Yes. So the air gap itself, the length of the air gap should be, this is the length right there, should be much smaller than the physical dimension of the core, right? Why? Well, because if it's compatible, then you're going to get so much leakage, right? Flux through this air gap, right? So this air gap has to be tiny compared to the physical size of the core, okay? So that's the condition, and that's what we do in practice, right? In the real world, that's what we do as well, right? And because of that, right, because L of G, which is the length of the air gap, is much smaller than the physical dimension of the core itself, then for calculation wise, the air gap is typically ignored, right? So LC minus LG is just going to be approximately LC, right? If you go back to this picture right there, let me erase this, right? And here is our LC from here to here, right? That's our LC, right? Without the air gap. With the air gap, that's going to be LC minus LG, right? So this is LC without air gap. Now, as soon as you introduce air gap, the length now, the new length, LC new, will be equal to LC divided by LG, right? However, since L of G is much smaller than LC, LC new is approximately equal to LC old, okay? In magnetic circuit calculation, air gap is treated as another reluctance in series with the reluctance of the magnetic core. So right there, right, it's just going to be another reluctance in the core, okay? And how do you find the reluctance of the air gap? Same as the reluctance of the core itself, except now the mu is just going to be mu naught. Whereas for the magnetic core, as you already know, mu is equal to mu r times mu naught, right? Okay. However, that's one thing, right? Mu naught versus mu r mu naught. Another thing is that the area of the gap, right? That's going to be different from the area of the core, right? Due to the fringing effect right here, right? So if you go back to this picture again, right? There's the cross-sectional area of the core right there, right? But in the air gap itself, the effective area, right, within the air gap is going to be slightly more than the effective area of the core, right? Why? Because of the fringing effect, right? What is fringing effect? Right here, due to the sudden change in the density of the materials from the core material to air. And by the way, this doesn't have to be air, okay? Just because this example use air doesn't mean that any air gap will be filled with air. It could be with any other material, right? From the core material to air, some of the flux will not take a direct path in the air gap, right? As a result, the cross-sectional area of the air gap needs to be corrected, given an additional percentage, right? For example, 5% more than the area of the core, right? So that's going to be 1.05, the area of the core. Right? And there's kind of like an illustration that I try to draw, right? Side view. Here's the core, right? And there's the other part of the core, and there's the air gap right here, right? So you can see the flux because of the fact that it has, what do you call it? Different mu, sorry, the same mu naught, but different mu, right? Much smaller mu, right? Close to 1. Therefore, the flux is going to be bent, that way, right? Instead of contained straight, down to the other side of the core, right? So because of that, right? Because of the expanding path of the core, therefore the effective length, the effective area of the core of the air gap would be bigger than the effective area of the core itself. Make sense, hopefully? All right. So here, any questions, by the way? No? All right. So then here's an example. I'm going to do this quickly because we stop at 3, right? I believe. So here's the example where we have a core with air gaps, right? So all you need to do here is to introduce another R for this air gap and another R for the middle air gap, right? And the rest is going to be the same as before, right? You have 3 segments, right? 1, 2, and 3. Now you have 2 more reluctances, right there. See that? Before you only have 3. 1, 2, 3. Now you have air gaps, right? So that's going to be represented by their own reluctances right there, okay? And I'm not going to go through this example, right? But once you realize that, yeah, oh, that's just another reluctance, then you can just add them up, right? Then this becomes just 1 R, and the center one becomes just 1 R. Then it's going to be the same exact problem as before, right? As the previous example, right? Just like that. See that? Okay. Any questions on this? Tedious, right? So at the end, you have the answer. So please go through those examples, okay? Those magnetic circuit examples. Those are just review for you, right? Making sure that you still remember how to deal with magnetic circuits, right? Using electric circuits, electric circuit analogy. Okay. All right. So what I want to do next is to spend the rest of the lecture today with going over or discussing air gaps, right? Now, why is it that we need to learn about air gaps, right? We learn about the concepts, right, on how to deal with the air gaps, but why, right? Well, the main reason, right, for example here, the major reason for why we need to learn how to deal with air gaps is because in many shapes of the cores, having air gap is unavoidable, right? So you have to have the air gaps, right, in many shapes of the cores. This is toward the end of the book, right? And the appendix, you can see I have appendix A that shows you different core shapes. Check this out, right? If you are using a UI core, for example, you see UI core right there? It consists of 2 different pieces, right, that you put together as a core, right? So the core by itself is not just one piece, right? You have to put 2 pieces together like that, right? So because of that, then again, you're going to have air gap, right? Which is very tiny, right? It doesn't matter how good or how well the 2 are being pressed against each other, right? But then you still have, that tiny air gap between the 2 pieces. Okay. Same thing with the UU core, the CUT-C core, right? You can see that for this example, having air gaps are something that you're going to have to deal with anyways, right? Okay. And There's more examples. Cut cores, right? Look at those cores. Well, this one is a solid one piece right there. Okay. But look at the other ones, right? Air gaps, right? All over the place. Okay, so that's the reason why. That's the major reason why in 255, I don't know if they tell you this or they told you this, but you know, cores, right? Most cores, they come with more than one piece. And you have to, again, construct the entire core from multiple pieces, or two in this case, right? Not that one is one piece. Let's see. That's cut cores again. This is the one that we have in our lab. Hang on. Which part is this? I don't think we have that one. I don't think we have this type of core in the lab. It looks similar, right? You can see that the cross-sectional area is square, right? In the middle, and rectangles on the sides, right? The one that I have in the lab is the one that have a circle in the middle, right? It's EFD or ETD. ETD, that's the one right here. This is the one, ETD. So this is the type of core, one of the types that we have in the lab, right? Really unfortunate that we don't, we not in the lab right now, because I just got a donation from, what's the name of that? Worth Electric. They sent me one rack of multiple types of cores as well, specifically for this class. I asked them if they can donate, because they're expensive. These magnetic cores are expensive. If you can donate cores for us for this class, and they did. So they were very generous. Giving us a lot of cores, and they are expensive. And the thing is, these are very brittle. They easily break. And every times I teach this lab, some groups are always not being careful. If you drop this on the bench, that's it. Forget it. It's gonna crack, right? And then it's gonna just it's just gonna break, right? I will talk more about all of these once we get into inductors. Right? I just want to show you the different cores at this point. So ETD, we have that in the lab. Pot cores, we also have this in the lab, this type. Right there, it looks like this, right? And then again, you put two pieces together, right? Oh, sorry, that's the top piece of the core, and that right there, and then that's the bottom piece, right? So because the core comes in two pieces, then of course that's going to be air gaps, right? And that's it. Looks like these are just the bobbins or RM cores. Yes, that's another core that we have in the lab. This shape right there. So that's the cross-sectional area from the bottom view of the half of the core. Again, it comes with two pieces, right? Two different pieces that you put together. Same thing with PQ. PQ is also two pieces, right? So that's just half, the top half, and the bottom, or one half. The bottom half or the other half is going to be exactly the same as this. So imagine that this is for this one half, and the other half is exactly the same. So you're going to press the two together, right, to make the entire core. So we have that. PM, I don't think I have PM cores. EFD, no, I don't think we have EFD. So it looks exactly like this, EFD. Again, two pieces. See that? Two pieces. And then EP. EP, do we have EP? No, we don't have EP, of course. Right. Again, there's two pieces, right? You see, many of these cores are having two pieces, right? They have two pieces to make the entire core. Okay, I think that should be enough examples for you to know the importance of why, or to know the reason why you learn about air gaps, right? Because again, it is unavoidable when you make an inductor or transformer to have air gaps. Let's see. they hold off core saturation to a higher value. And so that's one objective of having an air gap, right? Is that with an air gap, you can actually push the saturation point to a larger field intensity, right? I'll show you the picture later. And then also with an air gap, you could, the inductor or the magnetic transformer or inductor could actually store more energy, right? I'll just show you the picture. Right there. So this is without air gap. That's the BH curve of the core without the air gap. But if you introduce an air gap, look at what happens, right? It becomes this BH curve. So what is the importance of shifting or not shifting, but reshaping, right? The BH curve to be this way. Well, number one, you look at the saturation point, right? Before this core saturate quickly by that amount of current, right? It saturates already, right? Here you can extend the saturation point to a lot more current. See that? So it takes a lot more current to saturate the core simply by adding an air gap. Okay. Now look at the slope. Look at the slope. Look at the slope on this BH curve. Very steep, right? But look at the slope after you add the air gap. Right? That slope now becomes less or slower, right? So, or smaller, right? So the slope is smaller. And do you know what that slope means? Or what is the slope equal to in the BH curve? That slope is equal to mu, right? So the same thing here. So we have mu before and mu after. And you can see that mu after the air gap is slower or smaller, right? So then if you go to I believe previous chapter, right, when we have the equation for energy stored in the core, which I rewrite right here. Look at the equation for the energy stored in the core. 1/2 the volume times b squared over mu. So it turns out that energy stored in the core is inversely related to mu. So if mu is smaller, that means the same core can actually store more energy. Isn't that interesting, right? So these are the reasons why we use air gap. There's more actually. There's more reasons why we want to add air gaps, right? So such as flyback transformer, right? In a flyback transformer, we want the transformer to store energy, right? Almost like an inductor, right? So for a flyback transformer, we deliberately add air gaps, right? Why? So it can store more energy, right? Now you know the equation that demonstrates that, which is this equation right there, right? Because again, energy stored in the core is inversely related to mu. By adding air gap, mu becomes smaller because the slope becomes slower, right? The slope. Okay. And then this is also important, right? With air gap, as I said earlier, as you can also see from the picture, because the slope is slower, therefore it takes more current to saturate the core. It takes more current to saturate the core. Right? So that's those are advantages, right, of having air gap. Now, if I go back to this point, right, remember I said earlier about flyback transformer needing air gap. So we deliberately introduce air gap. How do we do that, right? So in the lab, what we do in the lab is, people or I ask students to put Kaplan tape, right? So between when they put together the two cores, for example, right? Instead of air, I ask them to put either paper or Kaplan tape in between the two cores, right there. And there's actually some calculation involved in terms of how much air gap that you like to have and how many layers of the paper or Kaplan tape that you need to put on those air gaps. Okay, so that's going to be later in the quarter when we have a lab on flyback, an experiment on flyback transformer. So we're going to learn more about that, right? Determining the air gaps. Okay. Air gaps also stabilize the inductance value for both bias and manufacturing variations, right? Again, that relates to the slope right there, right? Mu, right, is also related to L, or right here, that's the equation right there. Right there, that inductance is equal to N squared times mu A over L, right? So therefore, mu is proportional to L, or L is proportional to mu, right? The lower the mu, the lower the inductance, right? So basically, if you compare these two pictures right there, before and after air gap, the one before air gap has bigger inductance, whereas after you add air gap, the inductance drops, right? Because it has slower mu, right? Or a lower mu. Make sense? Now, from that point of view, that's a disadvantage, right? So now you know the disadvantage of having air gaps is that once you add the air gap, the inductance drops. But so from that point of view, it is a disadvantage. But look at in terms of stability, right? How stable the inductance is. If you look at the one on the left without the air gap, you can see the change, right, in the inductance. Right? Not the change in the inductance, sorry. Yeah, the change of the inductance, right? Because the slope is actually, if you zoom in, right, the variation is fast on the slope right there, right? Because it's very steep, right? So between small currents, right, if you just add a little bit of current, then the inductance will change so much. Whereas here, right, if I apply the same change in the current, like tiny change in the current, but that much, for example, right, then you can see that the slope is pretty much the same, right? So it's more stable. The inductance more stable with air gap than without air gap. That's an advantage, right? So now you know several benefits of adding air gaps, right? And one disadvantage. Well, what was the disadvantage? Lower inductance. And that has another physical implication, right? Or real world implication. When you have lower inductance, that means the impedance is going to be lower right here. Because I know that reactance, right, or impedance of the inductor is going to be a function of L. X of L is equal to omega L. So when you lower mu, then you lower L. When you lower L, then you lower the impedance, right? For the same voltage, if the impedance is lower, that means current is higher, right? So another disadvantage of introducing air gap is that the excitation current becomes bigger. What is it? Something like that. All right, there. The size of air gap has practical limitations since the air gap lowers impedance, resulting in increased magnetizing current, right? That's the same as excitation current, which is inductive, right? So they're not exactly the same, sorry. Remember these, but they're related. This model, right? Right there of a real world transformer. Here's excitation current, IEX, and here's the magnetizing current, IM, right? So this inductance right there, right, that's going to be a function of this mu, right? So mu is smaller, this inductance, Lm, will be smaller as well. If it's smaller, then per given voltage applied to this transformer, that's going to be more current flowing, right? And this is not a good current to have because that's a current that this is the current that is not being delivered to the winding. See that? Right. So that's taking away a portion of the current that is being actually used by the load. If I connect the load on the secondary side, right? So you don't want excitation current, which translates into magnetizing current, to be big, to be small, right? Any question on that? So that's another disadvantage is that when you add air gap, then inductance gets lower. When inductance gets lower, then magnetizing inductance gets lower. So therefore, the reactance of this magnetizing inductance gets lower as well per given voltage applied to the transformer, you get more excitation current or more, and also more magnetizing current as a result, right? So that is not good. That represents again another disadvantage of air gap. Now here's another interesting thing about air gap. Okay, I've already talked about how air gap elongate BH curve, right? So it makes it harder to saturate the curve, saturate the core, right? So we've seen that earlier. But if you gradually increase the length of the air gap, you can see that B max stays the same. See that? Stays at the same point. What's changing is H, field intensity. Right? The level of the flux density stays the same, but magnetic field intensity goes higher with air gap. That's the first thing. Any question on that? The second thing is this. Look at this part right there. Right? You can see that. What do you call that? Residual, not residual. I forgot the term now. Sorry. There's a term for that. The name escapes me right now. Can anybody remember the name? Phenomenon? I don't remember the name. I'm sorry.
Which one were you trying to remember?
These 2 points right there. These points. Coercive. There you go. Coercive points. Now I remember. Coercive. The coercive points, they stay the same. Look, doesn't matter how whether or not you add air gap, those 2 points, coercive points, right? They stay the same. See that? So that's what's interesting about having air gap. The flux density stays the same, not flux density, sorry. The maximum flux density stays the same, and the coercive point stays the same as well, as you are increasing the length of the air gap. Okay, so you can see, how do I know it's increasing? You can see A is 0 air gap, B is 0.01% of the length of the core, right? C is 0.05, so it's increasing length of the air gap, right? Make it more and more toward the right to the right of the graph, right? Making harder and harder to saturate by increasing the length of the air gap. Okay. Any question on this? Okay, I have 5 more minutes. This last 5 minutes, I want to talk about inrush current. This is another advantage of having air gap, right? We've talked about several advantages already with air gap. Another advantage is that with air gap, you can reduce the amount of inrush current. When you first start the power, right? When you first turn on the power, current will go through this winding. And at the very beginning, right, you're going to get inrush current. Why? Because flux has not been established yet, right? Initially, right? That's actually the best case. There's actually a worst case, right? We learned from the previous chapter that flux, right, is the integral of voltage, right? So if you apply sine wave, right? Imagine this is a sine wave, right? V of t is a sine wave. Theoretically, flux of t with respect to time inside the core should be a cosine function, right? Which it is, but the thing is, when you first start the power and the core is not magnetized yet, the flux starts from 0 right there, right? So the flux starts from 0. And then as voltage increases, flux increases, and flux increases from that 0, right? Following sine wave, see that? Or cosine wave in this case, right? So rather than doing this at the beginning, following this, right? It's not going to do that, right? Because at the beginning there is no flux yet, so it's going to build the flux first. Right? It's going to start from 0, and then gradually, right, it will take time. Once the flux, it's not dying off, sorry. Maybe here. Uh-oh, glitch again. I hate that. So start from 0, and then eventually, once the flux is established, on steady state, you have the cosine function that you are expecting. Okay? But in the beginning, I kind of exaggerate the sine wave there, the first one. But you see what I'm trying to say there, right? At the beginning, you have no flux, so therefore it has an offset first when it goes into the first cycle of the sine wave, right? It will have to have that offset, and then after some time, that offset is gone, right? Once the core already established the flux, then in steady state, you get this flux waveform in the core where the offset is gone, right? And because the swing has some offset, if you reflect that into the BH curve, you can see that the current goes up really high. See that? Really high. So that's what's causing the inrush current. And that happens only for a short moment of time, right? But still, it could be damaging, right, to some components that are in series with this transformer or inductor. And this gets really worse. So that's not the worst case, right? That's already bad. The worst case is when you operate the transformer already, and then you turn it off, and then the transformer is not, the core is not reset yet, right? So it has this remnant flux right there, right? So that's actually worse than 0, right? At least in the previous case, you start from 0 and the offset starts from 0. When the flux has remnant flux, then you see the offset is worse because now you shift the offset higher at that remnant flux. So now you get even worse inrush current. You see the current now goes way into the saturation region. You see that? It's even bigger current. So that peak current right there, right, that represents our inrush current. Okay, so how do you reduce the inrush current? And then we can adjourn after this. Introduce the air gap, right? Because air gap will be able to reduce that amount of current. And of course, the larger the air gap, the lower the inrush current. So that's where I want to end this today. So right there, what is it? I should have a picture of that right there. So without the air gap, you can see the inrush current at the beginning, pretty high. But then after the air gap is being introduced, the inrush current at the beginning is pretty much gone, right? See that? Okay. That is it for today.